Hello everyone. Today I'm going to be working on WebWork Homework 5, Problem 4. The reason I decided to pick this particular problem was that the actual calculations are not that hard, but it does take a bit of thinking to realize what it is that's being asked. So you've got, for the first part, it says a tank contains 70 kilograms of salt and 1,000 liters of water. Pure water enters the tank at the rate of 10 liters per minute. The solution is mixed and drains from the tank at a rate of 5 liters per minute. When you look at this, keep in mind that what's entering the tank is pure water. There's no salt entering the tank. There is only salt exiting the tank when it drains out. So, what is the amount of salt in the tank initially? Well, that's simple. That's just 70 kilograms. That's what it says right in the initial condition here. For part B, it asks you to enter an expression for the total amount of brine in the tank at time t. So the total number of liters of brine, you're starting out with 1,000 liters, and then each minute you're adding 5 liters of water, of brine, I should say. Yeah. Now, for part C, I made a mistake. I should say this is the amount that comes in. What this actually is the amount of water entering the tank, the 10 liters, minus the 5 liters that drain out. So this actually should say, comes in, or this should be in. Alright, so now the third part, part C. Let A represent the number of kilograms of salt in the tank at time t. Enter an expression for the concentration of salt in the tank at time t minutes after this process starts. Okay, so what happens, the concentration is really just the amount of salt divided by the amount of brine. Now we already know they said to consider the amount of salt to just be A. So the amount of salt part, you just enter A, and the amount of brine we've already calculated. At time t, it's 1,000 plus 5t. So we've got A over 1,000 plus 5t. Now for part D, we're setting up the differential equation. And this can be a little tricky. Now, a differential equation, in this case, is just how much salt is going in, subtract out how much salt is going out. Now, the thing is, the salt going in, like I said before, pure water is entering. There isn't going to be any salt in the pure water. So the in part is just going to be 0. Now you've got the salt going out. We've already got the concentration of salt right here. We've got the A over 1,000 plus 5t. But the amount of salt is the amount of water, right? The amount of brine that goes in times the concentration. So we've got a total of, like I said before, 5 liters. You've got 5 liters draining out at any particular time. And then you multiply that by A over 1,000 plus 5t. So you would have 0 minus 5a over 1,000 plus 5t. And you'd end up with negative 5a over 1,000 plus 5t, which you can then simplify to be negative a over 200 plus t. Once you've got that equation set up, the actual differential equation is relatively easy to solve, because you just have to take this term, move it over, and then you've got dA dt plus a over 200 plus t equals 0. And then you can find your integrating factor. So we've got p of t is 1 over 200 plus t. Mu of t becomes e to the integral 200 plus t to the negative 1. I like to, instead of using 1 over 200 plus t, I like to use to the negative 1. It reminds me that this is going to be an ln. E to the ln absolute value 200 plus t equals, you can just, e to the ln is just whatever's inside. And then you've got absolute value 200 plus t. Now, for what we're using, t is always going to be, it's going to start out at 0, and it's only going to get more positive from there. This function, absolute value, 200 plus t, this part inside, is going to start out at 200 when t is 0, and it's only going to get more positive from there. So instead of having this be in the absolute values, we can just have it out of the absolute values. These are going to be the same over the period of time that we're looking at. So always keep in mind what it is you're trying to model. So now we can now that we've got our integrating factor, we can say, the derivative here. We've got d dt 200 plus ta, and then on the other side, we've got 0 times 200 plus t. Well, there's a 0, so it's still 0. Now, we integrate both sides. This is just what's inside, 200 plus ta. And on the other side, don't forget the c. So 0, the integral of 0 is not 0, it's 0 plus c, because everything is plus c. So don't forget the c. I forget the c all the time, and you'd end up with a equals 0 if you didn't do that. So don't forget the 0. Or don't forget the c, I should say. So you've got a, you divide by both sides by 200 plus t, you get a equals c over 200 plus t. That's our general solution. And then you plug it in. We set our initially at t equals 0, you've got 70 kilograms of salt. So 70 is c over 200 plus 0, because t equals 0. And we can solve for c, that's 14,000. And then we plug our 14,000 into c, so we get our particular solution. A is 14,000 over 200 plus t. For part F, it is asking us how much salt will be in there at 3 hours. So why did I put 180? Well, this equation is for t minutes. Okay? So it's going to ask you to put the number of minutes that you need. So it's 180 minutes, not 3 hours. If you plugged in 3 for here, you would get the wrong answer. So you've got 14,000 over 200 plus 180, which is t, and you get 700 over 19. Now, for the last part, it's telling you, as t approaches infinity, what is this value going to be? Well, obviously, this t is just going to get bigger and bigger and bigger, right? Which means this term is going to get bigger and bigger and bigger. But since it's in the denominator, the total thing is going to get smaller and smaller and smaller until it's going to approach 0. All right, I hope this helps. Thank you.